Hi everyone, and welcome to the video on section 6.2 on volumes. So in this video we're going to be talking about how to find the volume of certain objects. So everything we're going to talk about, we are going to need to use this idea of taking a function, so the graph of a function, and rotating it about some axis. So there's a lot of symmetry in the shapes that we're going to be dealing with. Right? Just because that's the method that we have really relies on that. So down here we have this first definition, the definition of volume, which maybe seems, kind of technical if you read through this. So it says, let S be some solid. So you're just thinking like a three-dimensional object, filled-in object, that lies between x equals a and x equals b, which is kind of like, what does that even mean? Right? How do you lie between these two x values? So all it's saying here, and this is a little bit tricky because this takes some three-dimensional thinking to really kind of to see fully, and we're not going to have to really rely on that too much. We're going to do pretty much all our work in just the 2D, what we're used to in calculus. So we're going to do most of our work here in x and y. This is where we're going to do the work. But in reality, the shapes we're going to be dealing with are in this three-dimensional plane, z, y, and x. So when you get to Calc 3, you'll be dealing with this much more often. We're just going to kind of peek at it, but really we're going to work here. So what it's saying is your three-dimensional object, your solid S, is finite in some sense that if I took it, I could kind of go like this. Here's A and here's B. And the whole solid, if I kind of cut everything right here, like I just kind of sliced, the solid, it could be up in Z or over in Y, but at the very least, its X direction values are in between A and B. So I know, okay, it's sitting between A and B in the X direction. All right? So that's all that means, is that I've got a position on it. I know where it is. It's somewhere in here between A and B. Okay, so then this says if the cross-sectional area of S in the plane P sub x through x and perpendicular to this axis is A of x, that's a sentence if I've ever seen one, and it's not even done, where A is a continuous function, then it gives the volume. So what you have to understand here, and we'll see it in some examples later, kind of how these pieces fit in, but what we're going to be doing with our volume is we're going to be saying this, like, okay, let's say we have like some kind of lumpy bread. This is, for some reason, some lumpy bread that we have here. Okay, here's our lumpy bread. So we might be interested, like, well, what's the volume of this lumpy bread? How much bread do I actually have here? Well, there's a couple ways that we could do this, but in this class, what we're going to do is we're going to just say, you know what? In order to do this, here's what I'm going to do. I am going to cut this lumpy bread into some slices. And then what I'm going to do is I'm going to find the volume of each slice. And so what we do is we just say, I make a cut along here, and then I cut, and then there we go. So like this slice of bread is a little bit easier for me to handle. It's not as lumpy itself. It might be, a pretty nice shape. So that this, if I kind of take this and pull it out, it might be something with a lot nicer shape where I'm a lot more confident finding the volume of this thing. So this might be the slice I just cut out of here. And looking at this, it's like, even though I kind of messed up the drawing just a little bit, but just looking at this, it kind of just looks like, oh, I've got some squares, maybe rectangles. This isn't too hard to find the volume of, right? All I have to do is, just like with any box, is I have to do length times width times height. And I could get the volume of this, right? So the volume of this little piece would be length times width times height. Because let's just say we cut it enough so it's not really very bumpy anymore. in any one slice. The bumpiness is kind of the whole big bread has these curvy bumpiness to it. But when I cut out a slice, it's pretty kind of straight here. So that's what this is doing. It's saying, how do I find the volume of this? Well, why don't I just find the volume of these little slices and then add them all up? So going over here, this symbol, this is a summation, says add. Okay. Now, what is it adding? Well, let's think about this. It's adding two things. An area, which is given by this area here of this rectangle. Okay, this is called a cross-sectional area. So I took my loaf of bread, I took the knife and I sliced. This face I get, this two-dimensional face I get when I pull the bread out, just like your regular bread that you're used to, where you put your butter or peanut butter or jelly or whatever you put on bread. That's this area I'm going to find. Okay, and then to find the volume, right? To find the volume here, I have to multiply by, let's pick out green, I have to multiply by this. And that is this little width here. When I took and sliced my bread, how thick did I make the slices? And you should stop and think about this because, and it's something we've seen before already with integrals, if I make really thick slices, then it's going to be harder for me to get the volume of that, because the thicker I make the slice, the more kind of wavy the top can be and the less precise I can be. But if I can do much smaller, thinner slices and more of them, then that bumpiness won't really be there in any of the individual slices as much, and I can more precisely get the volume. So this is just like when we did area. We did the integral, we defined the integral using the little rectangles, right? You make really thick rectangles and you're not going to do a great job approximating the area, but you get smaller and smaller rectangles width-wise, then you're going to do a better and better job. Same process. It's exactly the same process. We're taking this one big thing, we're slicing it up, and the thinner we slice it, thinner, so controlling this delta x, the width, the thinner we slice it, the more slices we have, number one, and number two, the better job we'll do actually approximating the volume. So that's what this is saying. It's saying, okay, add up the volume of each slice of bread. How do I do that? I take the area times the width. Okay, so that's the volume of this one slice. Add it up. And then what's this limit doing? Well, the limit, just like when we first defined an integral in Calc 1, the limit's saying, okay, well, you can do that for 4 slices. Let n be 4. All right, that's going to be okay. But if you instead had done 8 slices, you'd do a better job. And 100 slices, you do a better job. And 1,000 slices, you do a better job. So what is the best job you could do? You could let the number of slices go to infinity and see what happens. That is our definition of this integral, right? So to find the volume of a solid, in this set of ways we do this, because there's many other solids, we could use many other ways to do these things. But for this section, the way that we're going to kind of think about attacking this is we're going to say, okay, give me the solid. It's going to go from A to B. So right now, just to make that connection real quick, this solid, if it's sitting here, this is the x direction, and that's at x equals b. And then this over down here, this is at kind of coming out the back. This would be at x equals a. So just so that we kind of have a where are we? We start at x equals a. We start here, and we would start taking slices and coming down this way, all the way until we hit b, and we'd be like, okay, I'm done taking slices now, because there's no more bread left after b. So there you go. That is the idea of volume. And so we're going to find a couple methods for doing this depending on the shape that we get and the functions we get to make our shape. But that's the idea. I know it's kind of a weird one, but just make the connection back to Calc 1 integral. How we defined it, very similar. Okay. So we've got this idea. So there are two methods we're going to talk about in this section, and then in the next section there's another method that we'll discuss. So the first one is called the disk method. And it's all about using disks. So here's a disk. It's got some thickness to it. So we've got a disk, circle, with some thickness. So there's a little bit of thickness here, like a quarter, nickel, dime, whatever change you want to use. So, okay, what are we going to do here? Well, let's think about this. Find the volume of the solid obtained by rotating about the x-axis, the region under this curve. So, here's a picture here. We've got this curve, and we want to take this and rotate about the x-axis. So see this here. This is telling me spin around the x-axis, okay? And I want the region under this curve, so that's why this is blue here. So I'm going to take this chunk. You can think of this as like a two-dimensional piece of paper filled in that you cut this curve into. And then you're going to take this and you're swinging around the axis. And everywhere this paper moves through is part of your solid. Okay, so it's you get part of the solid up here, and then you start moving this through, and every single point you hit is part of your solid. So all the way through. Right? So it says we want to find the volume of that thing that we get. Okay? And then it also says to illustrate by drawing an approximating shape. So this is the picture you get. See? Right here. So think about this. Take this, move it up through the axis, right? Rotate around. So it's circular in some way because I'm doing this rotation. I get this blue solid. Okay, so how are we going to figure out what the volume of that is? Well, if we're thinking about the bread scenario, we have to cut this into slices, right? We just take a knife and literally just cut through this big blue object. And when we do that, we just need to think about what do we get when we take that slice out and we remove the slice. What are we looking at? And in this case, because we did this rotation, right, the circular rotation, we end up slicing and getting this circular shape here. So that's in red. So this here is our slice. Okay. So hopefully that's not too terrible to see. So, okay, when we do that slice, the idea here, using the definition above, is if we just did a bunch of these slices with this fixed width here, right, this fixed width delta x, and we tried to fill this up, that would do a pretty good job filling up the entire shape. And so we could just add up the volume of each of those slices and we're all done. That's the idea. So, okay, let's do it. What did the theorem said? Or the formula say? It said integral from a to b of the area of a slice dx. So again, at every x in here, I get a slice. I can calculate the area. Cool. I can multiply by dx, which is kind of how you can think about it. This is acting like dx in the integral. It's not the perfect way to think about it, but it's pretty good. So this delta x here acts like dx. A of x is this area of a slice. This here is a of x, the way we think about this. So I multiply these two, I get the volume. Now just do that a bunch of times as you go from a to b. So what's a to b? Well, looking at this, it looks like I hit 0 here, which we can confirm because we hit 0 here. So okay, this is going to be 0. Okay, and then I go up to 1, which is a little tough to see here, but it's just going to be this point, right? So your original graph of the function is helpful. So 0 to 1, got it. Okay, now we got to think a little bit. What's the area of this object? Well, we already talked about how it's circular, right? So, okay, the area is going to be the area of this circle. Well, I know that the area of a circle is pi r squared. Okay, so then we just got to think about this. Like, okay, r, what's the radius of this? Well, just draw it. Say, okay, I'll just draw it. So here I am in the center, radius, and I hit right about in here. Okay, what did I hit? Right, I started in the center and I drew up. What did I end up hitting? I hit the function, right? What's this top curve here? That's just the function. So what's the radius? Well, at any x value, it goes from 0 up to square root x. So in this case, r is square root x, the function itself. And you might think like, well, how come the radius isn't just one fixed number? Well, think about this. If I choose a different x value, watch, I'm going to choose a different x value here. Here's a different x value. So what will I do here? I could draw in this little disk that I'm approximating with, but all I really need is what's the radius of that disk going to be? Well, for this little x, it's square root x, because that's what I bump into. I got to stop there. So no matter what x I pick in here, the radius of this, so you could say circle, but it's not a circle because of its thickness. Technically, it's a cylinder, right? It's just a very short cylinder. But in any case, the radius of this cylinder here is going to be just from 0 up to square root of x for that given x. So then what's the area going to be, a of x? Well, it's going to be pi r squared, but r was root x dx. That's 0 to 1 pi x dx, which is, remember, x to the 1, we add 1, divide, so that's pi over 2, and then we end up with x squared from 0 to 1, plug in the 1 squared is 1, plug in 0, woohoo, cancels, pi over 2. There you go. That's it. So you're done. So let's think about this, right? Review the steps. This problem, what are you going to do? You're going to take the curve and graph it between the x values they give you. Great. You're going to think about where you're rotating, because we're going to rotate about y later. We're going to change up how we rotate, so we're going to think about that. But x-axis, so I draw this little, okay, I'm going over this way. All right, then I try to think through what this picture is going to look like. Now, you don't actually need to be able to draw this three-dimensional picture. Here's what I do when I have trouble with that. So I'm going to show you what I do whenever I kind of get into a little trouble with trying to draw like what the 3D picture will look like. So I take, let me change up the color here so it kind of matches. I go, okay, here was my curve, right? This was the curve that I was dealing with. So I'm just replicating this picture. So I say, all right, what am I going to do now? I'm going to wrap around this axis. So I say, okay, great. So what I do for myself is I say, okay, what's that going to look like? And then what I do is I take this and I do this full 180 over the axis. So I don't go the full 360, right? I don't whip all the way around and get back here. I just go 180. So watch what happens when I do that. I'm going to take this and I'm going to rotate it down here. Okay. So, hopefully that looks like a little bit like this picture, right? The three-dimensionality of it is gone, but you kind of see the outline of the shape. Then from there, I'm like, okay, I can figure out what the picture's going to look like here. Pick an x value, right? And then look, we just get this picture here. So we just end up getting, boom, boom. It's not as nice as theirs, of course, but it's okay. Boom. So we end up getting now this same shaded idea that's kind of wrapping through here. And from this, we can get the radius without too much trouble. Because again, you can just see it. It's up and then bonk, hit the function. So if you have trouble drawing this three-dimensional thing, totally fine. Take what your original region, rotate it halfway, not all the way around, just halfway, draw that in, and you can still get equivalently this picture. So sometimes I do that just to kind of help myself. And I'll show you that again later with other examples. All right, let's keep going. Okay, next example is we're going to rotate about the y-axis. So not too much changes here when doing this. We just have to think about the variables we're using, really. So find the volume of the solid obtained by rotating this region about the y-axis. So this one's different in that it didn't actually give us any specific numbers to bound, right? Go back up here. Between 0 to 1. Okay, so I knew exactly kind of where to draw this. Here, I don't have that. I just have functions bounding. And so this is something I need to be able to graph, draw, whatever. So that's down here. We have y equals 8, cutting through here. Y equals x cubed. See that? Cutting through here, okay. And then x equals 0. So I'm stopping at this point here. So that gives me this shaded region in blue. Okay. So again, you're having trouble maybe drawing this out, kind of this 3D picture we're about to get here. That's okay. Just take what you have here and, again, rotate it half the way. So that would be something like this. Okay. Then you're going to have this cutting through here, and so again, hopefully we see it's like, okay, we're rotating around, so it's like a disc again. Cool. Let's color that in, so it's a disc. Now, okay, what's the radius of this disc going to be? Well, start in the middle here, and then we can go out, and then bonk. Okay, what happened? We hit the function. What function? So this is where we have to be a little bit careful, because you might just be like, okay, r is x cubed, hooray. But wait, we got to think about what's going on here, because we're not actually picking an x value, right? If I was to replicate exactly what we did here, and this is a little tricky, but think about this. I pick an x value, then I draw in the cylinder. But look, this is important. The cylinder is vertical, and you can picture the cylinder moving as I move the different x's. I get the cylinder that kind of slides along the x. But is that what I have here? No, I'm not picking an x value. I pick a y value, and then hopefully you can kind of see, and maybe it's easier here. The cylinder, changing size, of course, as you go, would be sliding along here. So I'm sliding along the y, which means y must be my variable for the integration. It's the variable that I'm picking each time. It's the variable that is going to go into my area formula. So in this scenario here, I need things to be in terms of y. So this is important. In this scenario, because my disk is horizontal, right? My area is going to be a function of y here. So in this case, I've got a horizontal disk, and so that's telling me, oh, horizontal disk. That means it moves up and down. So, okay, area has to be in terms of y, which means this is no good. My radius has to be in terms of y, which means we solve for y, and boom. So, tricky extra thing. When you do this, you also now have to add to the list of things to do this little check of what variable am I going to be using here. And this is a little tricky, and unfortunately it can change depending on what method you're using. So we're using disk now, but next section you're going to see we use this thing called the shell method, and that changes up how we think about what variable to use. So a lot of processing has to go in before you even kind of really start with any integration. But once we have that done, we still have a disk, just like we did in the last problem. We still have this disk. We've got the area. We've got the height here. So this little width. So then we can plug it all in. Integral from a to b. Okay. What's our first y value? Right down here, 0. Goes up to 8. I can pick any y between 0 and 8 and draw in this little cylinder. Okay, what's the area going to be? Well, we already said it was, r was this, but remember we're doing a disk, so that's pi r squared. So let me square this, put a pi in, dy. Okay, so then we can take the pi out. This becomes y to the 2/3. And then we have our method, right? We know how to do this. Add 1, divide. So that's pi y. Add 1 to this, right? That's going to be 5/3. And then divide here would be 3/5. We're going to go 0 to 8. All right, so that 3 pi over 5, we can take that out. Then we're going to plug 8 into this. So that's 8 to the 5/3. And then we're going to plug 0 in, but that's just going to be 0, so we can stop here. Okay, so you can plug this into a calculator, but you can do it quick too. 8 to the 1/3 power is 2. 2 to the 5th, if I remember correctly, is 32. So then this is going to be 3 times 32, which is 96 pi over 5. And there you go. Okay, so boom, we got it. So when we're doing the disk method, if instead we're going to rotate around this y-axis, we have to change up our variable to y. Okay, let's try another one. So we've got the region enclosed by the given curves rotated about the specified line. Find the volume of the solid. So they give us 2 lines about the y-axis. Okay, so we graph this here in Mathematica. Again, I mean, you could do this by hand. It's pretty tough though, especially because I think it messes people up with now x equals. Because you're so used to y equals, it can kind of be tough to do this. But it's not the most horrible thing, because if you just kind of stop yourself for a second, you can do something like this. It's really not a big deal, just to kind of get your bearings. Just switch the variable so you can see it. Oh, like this is just a quadratic. So I'm just looking for a polynomial, or sorry, a parabola. This is just going to be a parabola. But remember, it's not going to be anything like this, right? Because that's y equals x. In order to go x equals y, we're talking instead. So then in order to kind of flip this around, we're going to be talking instead about a picture like that. Okay? So just to kind of help you think through how to see something like this. So we can do a little bit more too with this. Because we know that this is a negative y squared, right? That actually tells us the kind of orientation of this thing. It tells us that, you know, go back up here. Negative x squared, that's not this one, that's down, right? It's flipped down. So then this can be a little bit tricky to think about, right? But if you just think about it like this, when this is positive, right, I'm opening up to the positive y. Make it negative, I'm opening to the negative y. Do the same thing over here. If this was a positive y squared, I'd be opening up to the positive x. But since this is negative, I'm actually going to be going down. So our function looks something like this, which is this one here. So this is x equals 2y minus y squared. Now, what did we say when you're first drawing these out, right? You've got this shaded area here. Okay, how do I figure out what the solid's going to look like? Well, I'm rotating about the y-axis, right? So then I take this thing and I'm going to rotate it around this. And if you can't draw out the solid because it's a little too hard to draw, like 3D, go only halfway. That would be this curve. And then, okay, so like you get the kind of like general shape of this thing. So there you go. Now, we got to think about this. I need to fill this up with cylinders. So I'm going to be picking a what value? An x value? No, an x value won't work, right? Because then I'll have cylinders here that fill up these vertical cylinders. And it's not going to be super great kind of doing it, because then there's this huge range of them. And it's just not the best. I mean, you could try to do it, but it's not going to be that good. The much easier way to do this would be to pick a y value, any of these. Just pick a random one here, and then put in your cylinder. All right, we put in our cylinder. Whee! I'm not the most fantastic cylinder drawer, but hopefully it's not too bad to see. So there's our cylinder. Okay, so I picked a y here, right? So that means immediately, because I'm picking y values to draw my cylinders, I know that when I set this integral up, it's going to be dy. Okay. Again, I've just got a disk here, right? So then I know the formula. It's pi r squared dy. Okay, what are my bounds? Well, down here it looks like 0, and I hit x equals 0, so that's another thing to kind of help you kind of figure out what's going on here. When x equals 0, this is going to be 0. Boom. But then also up here, when x equals 0, this is actually going to be 2 as well. So that's another thing to kind of try to solve for. So okay, I'm looking at this. I got this picture. Great. So I can go from 0 to 2. Boop. Boop, boop. Okay. Any y value in here I can pick. And then I'm going to try to find the radius of this. But again, with the picture, it's not too bad. You got this here. Draw out. Bonk. What did I hit? Well, I hit the function. So then my radius is just going to be the function. Whatever y I pick, that's how far out I'm going to go. So let's draw this out. Give ourselves a little more room. This is the integral from 0 to 2, pi, and then it's radius squared. 2y minus y squared squared dy. All right, I can do this one. So I'm just going to multiply this out, do a little foiling, right? So I'm going to take the pi out, integral 0 to 2, right? And then you're going to foil this. So we're going to get 4y squared, okay? And then we're going to pick up these two multiplied would be a negative 2y cubed, but there's another one, right? So it's a negative 4y cubed. And then this times itself is going to be plus y to the 4th dy. So definitely write that out for yourself. Okay. Then I can do each of these individually, right? Because we know that we can break up this sum. And then this is just the power, the anti-power rule. However you want to think about it for each of these. The reverse power rule. Okay, so that's going to be pi times, add 1 divide, 4/3 y cubed, minus add 1 divide, y to the 4th, plus add 1 divide, y to the 5th over 5, from 0 to 2. Okay, so then we'll do that over here now. Pi 4/3 2 cubed minus 2 to the 4th plus 2 to the 5th over 5. And lucky for us, plug 0 in. That's just 0. Okay. So there you go. That's your answer, which you can plug into a calculator to simplify this down as just one number if you want. Go ahead and do that. There you go. So hopefully not too terrible. You got your picture here. You figure out where you're going, the y-axis. What did we say last time? Rotating about the y-axis using this disk method, I need y as my variable. That's the one that I just imagine I'm sliding this disk along the y, so that's got to be my variable in here. Find the radius and go. All right, let's keep going. So the next thing is what's called the washer method. So the washer method is kind of like the disk method, except sometimes we get solids where there's holes in them. So you can see in this picture, I know it's a little tough to see. It might even be easier just to picture this. If I take this here and I rotate it about this axis, okay, then all right, this blue is going to rotate through, and we can even kind of see it if we redraw this, like I said, to do halfway. So we'll do my best to redraw this here, and then that's kind of going to be like this. Boom. Okay, so that's me just kind of moving this 180. So I rotated only 180 degrees down here. So, okay, great. But there's a giant hole here. Look, all of this is not getting hit inside by anything. So there's a hole here. So if I try to put a cylinder in at some specific x value, that's not going to work. A cylinder won't work because this cylinder will try to eat up all of this inside as part of the volume, but it's not. There's a hole, so you can't do that. So what we do is instead we fill with a washer, because a washer has a hole in it. So the washer will be, actually exist in here. There'll be a hole, and then it'll come down and come through here. Okay. So in this example, we've got the curves y equals x. That's a straight line. Y equals x squared here. Again, I don't, give you any numbers, so just like in section 6.1, you got to figure this out, right? So that's x equals x squared. When do they hit? Well, so you could do this a bunch of different ways, but that's the same thing as 0 equals x squared minus x, factor. So they're going to hit when x is 0, boom, and x is 1, boom. Okay, so what are we thinking here? Well, look, I've got this vertical washer here, just like the vertical disc I had before. That means I could slide it along x, right? I could just picture this thing sliding, growing, and shrinking as necessary, but sliding along x. So I need things in terms of x. So I just because of that, I know that this is going to be a dx integral. Okay. So then we're like, okay, how do I find the area first of this? Well, the area of this isn't too bad. The area of a washer, you can break it up into two pieces. So the area of a washer is going to be the area of the outside circle. See how there's an outside circle? So A of x here is going to be the area of the outside circle minus the area of the inside. So you could just treat this like two circles and figure out the area that way. You don't have to go too crazy with this, like, oh, I got to do this washer thing. Nope, the area of this is outside minus inside. So what's different about this? I need to find two radii. Okay, I need two radii, the inner and the outer, which isn't actually too bad. Just draw the picture. So we've got our washer here at some point. So here we go. We picked an x. Here's our washer. So it's going to come through, boom, hit here. But then we've got this other one, boom, that hits here. Boop. And then this kind of comes back through and hits here. Okay. So we've got this washer here, and we're going to pretend, for the picture's sake, like I drew the radius in a reasonable place. Baha, there you go. So there's an inner radius, boom. And then let's actually do that green so it's a little easier to see. So there's an inner radius here, right? Bonk, what I hit x squared. So immediately, inner radius, Ri, is x squared because I just bonk hit it. Okay, what's the outer radius then going to be? Well, let's kind of look through here. Start again in the center, and I'm actually going to go below so you could see it a bit better, even though we're kind of going up each time. Past the inner radius and bonk. Okay, I hit y equals x here, right? That's this one, y equals x. So the outer radius is x, y equals x. So that's my two radii. Inner, bonk, hit x squared. Outer, bonk, hit x. Okay, so then this isn't too bad. We can do this, right? So we go down here, see some nice pictures, and we get integral. Now what were the numbers I went to? 0 to 1 I figured out, right? 0 to 1 of pi, outer radius minus inner radius. So let's go back up here. Outer radius is x. So then it's x squared, because remember I'm doing r squared, radius squared, minus this squared. Okay, because remember, right up here, outer radius squared minus inner radius squared. Outer radius was x, square that. Inner radius was x squared, square that. Dx. That's equal to pi, just take that out, 0 to 1, x squared minus x to the 4th dx. Okay, I can handle these, not too bad. Pi times, and then this is x cubed over 3 minus x to the 5th over 5 That's from 0 to 1. Okay, we can plug that in. We'll go over here. That's pi 1/3 minus 1/5, because remember the 0 just cancels in here. Okay, and so you can make these 15ths, right? So that's 5/15, 3/15, so that's 2 pi over 15. Boom. So hopefully that's not too much worse. You just got to find the 2 radii and then set it up outer minus inner. And that's hopefully not too bad to see if you just draw a picture. Okay. So let's try this one. So this says we've got y squared equals x. Again, another parabola. All right. And then we've got x equals 2y, which is just a line about the y-axis. That's where we're going. Okay. So let's think about this. I need a washer, right? Why do I need a washer? Well, if we go over and look at the picture, which to start drawing this picture for yourself, you'd have to go, okay, a parabola, x equals y squared. So this is going to be on its side opening up like this. That's right here. X equals y squared. And then I've got a line, x equals 2y. That's right here. Okay. Then what do? We rotate around here, so I draw myself this 180-degree rotated piece here. So this is the original. This is my rotated piece to kind of give me an idea what's going on. Okay, so it's like, all right, I can pick a point here, any point here, and I can try to draw in, and we're just going to draw it like this so I don't continue to make a fool out of myself. So there's a cylinder in here, but it's not really exactly a cylinder, right? Because what did I just do wrong? Look, I tried to color in all of this. I can't do that. That's no good. This inside is a hole. So instead of doing that, you try to draw that in. It doesn't work. You go, okay, there's a hole in here. So instead what I'm going to do is I only want to actually take up here to here, right? This is going to be a little bit of thickness here and here. And then that's going to wrap around, right? Wraps around. Okay, so first things first. I'm picking a y value. So that tells me dy will be part of my integral. Okay? Because I can slide this up and down and still get this washer. Okay, so then from there, I'm like, all right, find the radius. Bonk. What did I hit? I hit y squared first. So my inner radius is y squared. All right, let's get the outer radius. So you could still do it in the same place if you want. It's not too hard to see. Bonk. I hit 2y. Okay, what's my formula? Well, it's going to be the integral pi, and then we take the outer radius squared minus the inner radius is y squared, and then of course that gets squared, don't forget, dy. Now my bounds are when these are equal. When does y squared equal 2y? Algebraically, not too bad to solve. That's just 0 and 2, but do your practice there. Okay, so that's going to be pi integral 0 to 2 of 4y squared minus y to the 4th dy, which we can do that. Okay, so then add and divide, so it would be pi times 4/3 y cubed minus y to the 5th over 5, and that's from 0 to 2. Okay, so let's plug the 2 in. That's pi times 4/3 2 cubed minus 2 to the 5th over 5. Plug 0 in, I'm going to get 0. That's pretty nice. And then, you can simplify that down. But this is our answer. And there you go. So, hopefully not too bad. Draw your picture. Look at where the washer is. Figure out what variable you need. Find the inner and outer radii. Plug into the formula. Do your integral. Boom. So there is a different thing that can happen here that we have to explore, and that is right here, where we don't have to only do the axis of rotation as the X or Y axis. We can do any line here we want. We're going to stick to vertical and horizontal lines, but there you go. So this is our new axis of rotation, is X equals 1. So how do I do this? Well, just start it off like regular. Graph these two functions. So I've got x cubed, y equals x cubed, which is here. So here's y equals x cubed. And then I've got y equals root x. It's right here. Okay. Well, what are my bounds going to be? We can always start there if we want to. That's going to be x cubed equals root x. Okay. So you can square both sides here. X to the 6th equals x. This is going to be true when x is equal 0 or 1. So that means x is 0, x is 1. So boom, 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 boom. So okay, not bad. Okay. Then we have to think about the picture here. So again, I'm rotating about x equals 1. So you can draw that axis in, and then you're going to rotate around this. So again, what do? We take our original picture here and we rotate it halfway, right across this line. Okay, so now what we have to figure out is, am I picking an x value or a y value here? So what is important here is this rotation axis vertical, like when we were doing the y-axis, or are we rotating around a horizontal, like when it was the x-axis? Well, in this case, we're just like the y-axis here. We're going around and around and around, but this is a vertical axis. And so it's going to work just like it did before, where I am going to be able to pick a value here, like this, right here. Here's a y value. And then I can fill that up. So I can take a washer and now fill it in here. So let's do that. We'll pick this y value just as one to look at, no special reason. And then we're going to be able to fit a washer in here. So we've got the washer that'll cut through here and it'll cut through here. So we've got this little washer cutting in. It's going to slice through here and it's going to slice through here as well. Okay. So then we've got this washer that's going to kind of cut through here and here, but it's going to wrap all the way around, right? So what we need to do is find the radii. Okay, well that's not too awful. We've been practicing this. Start here, bonk, or you can go the other direction too, as long as you're just picturing which is the right function to hit. But what was this? That was this inside one, which is y equals x cubed. Okay, but we can think about this. This is in terms of x's. That's not what we want. We're doing y's here, right? This, I can slide this up and down, not the other way. So we need dy here, which means it's not a big deal. It just means you have to solve these functions now in terms of a function of y. So this first one will be x equals y squared, and the second one will be x equals cube root of y. So we need to find, because this is a washer, the inner and outer radius. Here is where this gets trickier. So the radii, RO, and then we can do RI. This is where this gets a little bit trickier. It's not crazy trickier, but it's a little bit trickier. Like, what are these going to be? Okay, so we start the same way, right? Boop. Go until you hit something. Bonk. Okay, we hit this function here, which was x equals cube root of y. All right, so what's your initial guess possibly? Oh, that's easy then. The inner will just be, okay, look at this. That's not too bad. I've been doing this the whole time. But that's not right, because if I plug in this y, this distance here will not be equal to this number. That would be true if I was starting down here at 0, plugged y in, and went like this. This would be cube root of y. Okay? Because whenever you're thinking, okay, what's the value of the function? You start at 0, right, and go up to the function. That's not what this is. I started at 1 and went down to the function. So how do I figure out what this distance is? Well, luckily it's always the same thing. As long as you got to think through it a little bit, but it's the same idea each time. This total distance is what? 0 to 1. Okay, so the total distance here is 1. I want this little tiny piece. How do I get this? Well, if I could just take the whole distance and subtract off this, I would get this. So I know it's a little weird to think about, but if I take away this distance from the full 1, I get this little tiny piece. So this is wrong. The actual answer is 1 minus the cube root of y. So again, if I want to plug y into this function here, right, this one right here, I get this full big distance, which is not what I want, right? That's not what I drew. I drew this one. So in order to get this tiny one, I have to do 1 minus that. So it's a little tricky. You just got to kind of think through it. Okay, so let's put that down. 1 minus the cube root of y. Okay, what about the outer radius? Let's try to think about that one. So the outer radius. Okay, so again, I'll pick a y value here. I'll go woo, bonk, hit that one. So you might again think, okay, so that's just root x. But again, nope. If I plug a specific y value in here, right? If I plug a y value in here, I'm going to get up and I'm not going to hit this root x function, right? Or y squared is the way we should be talking about it because that's what we're in right now. I plug a y into this, I'm not going to get this distance. I'm going to get this one starting from 0. So again, the outer radius is actually 1, because that's the full distance here, because I have this at 1, minus y squared. If I had to plug just y squared, I would only be getting this distance, which looks okay because of the point I picked. But if I pick this one up here, that's huge, when really I only want that. So you got to be a little careful. 1 minus what your intuition might be. So that's where this gets tricky with the axis of rotation, is our radii are shifted by this 1. See this 1 here? It's that shifting over. Okay, so once we're past that, though, it's really not too bad because we just have the integral from 0 to 1, which are my y values, 0 up to 1. And then it's pi times, okay, same formula, it's washer method, right? Outer minus inner. So 1 minus y squared minus inside. 1 minus root 3 of y squared dy. And then this is a little nastier, but it's not terrible to do. We just have to, again, multiply everything out, right? So then we can do that. That's 1, and then I pick up 2 of these, and then I get a y to the 4th minus, and I'm going to put this in parentheses so I don't mess up my negatives. So again, I get a 1, I pick up 2 of these, cube root of y, this times itself. Okay, that's going to be plus y to the 2/3 dy. Okay, and then I just got to kind of put all this together, right? So this becomes negative, positive, negative. So pi integral 0 to 1. 1 minus 2y squared plus y to the 4th minus 1 plus 2 cube root minus y to the 2/3. That's all dy. And then I can do each of these separately. I mean, you could combine these first, right? So maybe we should do that. Those go away. So, okay, after you do that, you get pi, and then we're going to add and divide. So that's going to be negative 2/3 y cubed plus y to the 5th over 5. Okay, so then this is going to be, again, this is just y to the 1/3, right? So that's going to be plus, add 1, that's 4/3, right? 4/3, flip it over. That's 3/4. So it's going to be 3/2 y and then 4/3 minus, add 1, I get 5/3, flip it. And that's from 0 to 1. 0, I plug into this, everything's going to cancel. So this is just going to be -2/3 plus 1/5 plus 3/2 minus 3/5, which I'll let you simplify. Boom. You know, these get a little bit more intense with the integrals when you're doing this shifting. But it's just a little bit more algebraic work and not much more than that. But there you go. So if I have this axis of rotation shifted off the y or x-axis, what does it change? It changes how I find my radii. These radii I might be kind of used to doing, just, oh, bump into the function, you're done. Nope, they are actually shifted off. So watch out for that. All right, so a lot to practice here. Again, a lot of stuff going on, but each individual piece isn't too bad. You draw your pictures, you figure out where you're rotating about, you figure out what values you're going to go between for the bounds, what variable you need to use, draw in a little washer, a disk, so you can get your radii, plug into the formula, do the integral. A lot of steps, but again, you just take it one step at a time, and you get this process down by practicing a lot. Won't be too bad. So any questions, as usual, let me know, and I'll see you in the next video.